Well, hey everyone! I am absolutely thrilled you could join us for today's explainer. For years, the story of deep learning has basically been a story of pure brute force. We're talking massive neural networks, chewing through literal mountains of data, all powered by these warehouse-sized supercomputers. But, as you might guess, that era is hitting a wall. Hard. Today, we're exploring a totally fascinating paradigm shift in artificial intelligence. We are finally moving away from that brute force approach and entering this really elegant, highly efficient future of what we call learning with less.
So here's our roadmap for this explainer. First, we'll look at the deep learning bottleneck. Second, shrinking compute and memory. Third, rethinking data and labels. Fourth, generative models and diffusion. And finally, predicting the unknown.
All right, let's jump right into part one, the deep learning bottleneck, and the frankly glaring unsustainability of modern AI. To really understand why AI research is pivoting so hard right now, we have to look at its insatiable hunger for manual human labor. Get a load of this staggering number, 312.5 days. That is exactly how long it takes, and we're talking working 24 hours a day, 7 days a week here, for a human to manually annotate just 5,000 images in a standard benchmark dataset called Cityscapes. Actually, if you factor in normal working hours and weekends, you're looking at 4 full work years for a single person. All of that just to trace exact polygon boundaries across millions of pixels, just so an AI can learn what a car or a pedestrian looks like. It's wild. Which, understandably, leads to this incredibly provocative question. Do we really need to manually click all 1024 by 2048 pixels in every single high-resolution image? The harsh reality of this manual labor bottleneck has forced researchers to invent some seriously ingenious workarounds. Spoiler alert, the answer to this question is a resounding no. But before we dive into how they fix the data problem, we've got to talk about the other massive roadblock in the room.
Moving right along to section 2, shrinking compute and memory, and how we bring these massive models to the edge. Because data isn't the only bottleneck, right? The hardware itself is equally unsustainable. Take a look at the harsh economic reality of this productionization gap. To do full fine-tuning on a modern large language model, you need top-tier enterprise GPUs, like the NVIDIA H100. That beast has 80 gigabytes of VRAM and costs over $12 an hour just to run on a cloud service. Meanwhile, if you look at a really high-end consumer GPU, like an RTX 480, it only has 16 gigabytes of VRAM. So the big question is, how on earth do we fit an industrial power plant of an AI model into the, relative pocket battery of a consumer device?
This brings us to a total game changer, parameter efficient fine-tuning, or PEFT for short. Think about full fine-tuning in AI like tearing down and rebuilding every single structural beam of a skyscraper just because you want to change the layout of a few rooms. It requires massive construction fleets and scaffolding, which in AI terms means huge amounts of memory for gradients and optimizer states. PFT, on the other hand, is like clipping modular adapters onto the existing walls while leaving that massive foundational framework totally frozen. You only train a tiny, tiny fraction of new weights. This drastically reduces memory usage, so the model can actually run on that consumer hardware we were just talking about.
So the crucial point is how we actually pull this off. One of the absolute most popular PEFT methods right now is called LoRA, which stands for low-rank adaptation. If PEFT is the broad concept of not rebuilding the skyscraper, LoRA is the specific architectural trick to do it. Imagine you're building an auxiliary bypass track right next to some existing super heavy factory machinery. You use this small bypass track to adjust the flow of the product without ever having to open up or modify the massive main machine. And because of the way the math elegantly works out, at the end you can just merge this small track linearly right back into the main system. The result? Your newly customized AI runs just as fast as the original with zero added latency. Okay, on to section 3, rethinking data and labels. Let's look at smarter ways to supervise AI. So, how do we solve that crazy 312-day manual labor problem we looked at earlier? Well, instead of manually tracing every single pixel, researchers developed something called interactive segmentation. You can think of this as collaborative clay sculpting. Instead of leaving a machine to carve a statue all alone, or a human breaking their back doing all the carving, the human just taps a specific spot with their finger to say, hey, add clay here, or shave some clay off here. The machine dynamically reshapes the boundary after every single tap. Using this method, just 2 to 3 guiding clicks per object can literally replace exhaustive manual tracing. But believe it or not, we can go even faster. The contrast in time cost here is just stark. Tracing exact pixel-level labels takes about 78 seconds per object, but simply tagging an image with a text label, like just saying, hey, there's a dog in this picture, takes barely 1 second. This massive time savings is the main motivation behind what we call weakly supervised learning. By using techniques like class activation mapping, or CAM, the AI actually learns to locate the exact shape and boundaries of an object just by looking at those simple 1-second text tags. It cleverly works backward to figure out which pixels were most important for triggering that specific tag. Another genius method to use less data is self-supervised pseudo-labeling. Okay, imagine a master artist creating an anchor sketch under perfectly clear lighting to set a flawless reference blueprint. That's step 1. The AI makes a prediction on a clean, weakly augmented image. If it's highly confident, that's step 2, it treats its own prediction as a hard fact. We call this a pseudo-label in step 3. Then, it's like apprentices attempting to reconstruct that exact master blueprint, but across heavily distorted canvas conditions, like pouring rain or thick fog. That's step 4. Forcing the AI to match that clean prediction on heavily, strongly augmented versions of the exact same image. Finally, it computes the loss in step 5. This whole pipeline teaches the model incredibly robust representations without needing any human labels at all. Let's pivot to section 4, generative models and diffusion, creating complex data out of pure noise. We are now stepping into what is arguably the most fascinating frontier in all of AI: how models synthesize photorealistic details out of absolute randomness. The secret engine behind modern image generation, things like Sora or Midjourney, is diffusion. Think of a single drop of ink falling into a glass of crystal clear water. As you stir the water, the ink drop dissolves outward into this uniform cloudiness. That's the forward diffusion process, taking a clean image and incrementally adding noise until it's completely degraded into static. Now imagine filming that dispersion and running the video in reverse. The model literally learns to pull those diffused particles back together step by step, iteratively removing the noise to generate a perfectly sharp, brand new image entirely from scratch. It's basically magic. And listen, this isn't just for making pretty pictures on the internet. It has absolutely vital real-world applications. Take medical imaging, for instance. Generative models learn the underlying distribution of what healthy anatomy is supposed to look like. It's just like a master art restoration expert working on a damaged canvas. Because the expert has this deep internal mental model of thousands of masterworks, they can look at a degraded, noisy MRI scan and reconstruct the missing details. Or even better, they can instantly spot foreign anomalies, like a tumor, that simply do not belong in the healthy composition. Which brings us to our final part, section 5, predicting the unknown, knowing when the model is unsure. You see, if we are deploying these highly efficient models into the messy real world, think self-driving cars or medical diagnostics, it is absolutely crucial that the AI can quantify what it does not know. To prevent catastrophic failures, researchers divide model doubt into 2 separate types. First is epistemic uncertainty. This is like exploring unseen map territory. The model simply lacks knowledge because it never saw this in its training data, like a classifier trained strictly on dogs suddenly being shown a cat. You can fix this by exploring the map and adding more data. Aleatoric uncertainty, on the other hand, is like looking through a foggy telescope lens. The data itself is inherently noisy or blurred. No matter how well you know the map, the measurement is just degraded. Knowing exactly which type of uncertainty we're dealing with tells us exactly why the model might fail. So how do we actually measure this doubt? One incredibly powerful way is using a Bayesian neural network. Think of a standard neural network kind of like a physical marble track, where every single piece is welded at rigid, fixed angles. A marble dropped in will always take the exact same deterministic path. But a Bayesian neural network attaches each track section with flexible, vibrating springs. It places a probability distribution over every single parameter. So when you drop multiple marbles in, you get a spread of different trajectories. If all the marbles still land in the exact same spot, boom, the model is certain. But if they scatter widely across the floor, the model's telling you, hey, I'm highly uncertain about this one. Now, once a model can measure its own uncertainty, whether that's by using ensembles or techniques like MC dropout, which randomly deactivates neurons during testing to simulate that vibrating marble track we just talked about, it unlocks something amazing called active learning. Instead of humans blindly labeling those 5,000 images for 312 days, the AI can look through the raw data itself and say, you know what, I am highly uncertain about these 10 specific images. Please just label these for me. It actively requests human help only for the absolute most confusing informative samples. And that right there is the ultimate loop of learning with less. We've seen how dramatically the paradigm has shifted today. AI is actively overcoming its biggest bottlenecks. It can adapt on standard consumer GPUs, it can guide its own learning with minimal human data, and it can even mathematically quantify its own ignorance to keep us safe. Which leaves us with this final, lingering thought. If AI can now do all of this independently, what happens when it starts asking its own questions? Thank you so much for joining me on this explainer today. Keep learning, stay curious, and I'll see you next time.